We're given here a set E, which is a non-empty set, which contains two subsets A and B, which are fixed, right? Now we've defined a mapping from subsets of E to subsets of E, and it's defined this way. You take any subset of E, and then you make the intersection with A, and then after that, you make the union with B. All right? Now we take this function to define a relation. You define the relation this way. Relation is called f. X is related to y if and only if f of x is equal to f of y. Right? And then we have to prove that this is an equivalence relation and then obtain the equivalence classes and the quotient set. Then we have to do a part B, but we will come to that later. So let's go to this. Let's try to prove this first. As a matter of fact, we're going to prove something more general than that. What we're going to prove is that if you have any relation whatsoever between the elements of any set, right, which is defined this way as a function of the first element equal to the same function of the second element with a given function, any kind of function, right, then this is always an equivalence relation for any function f that you put there. The reason is obvious, because f of x is equal to f of x, which means x is related to x. So it is reflexive, right? F of x is equal to f of y is a symmetric relation, because then f of y is of course equal to f of x. So that means f x related to y implies y related to x, which means it's symmetric. And if f of x is equal to f of y and f of y is equal to f of z, well, you can see in this chain of equalities that f of x is equal to f of z, which means that if x is related to y and y is related to z, then x is related to z, which means it's transitive. And you see, in this proof, we haven't used any other fact that the fact that these are two. This is an equality between the functions of the function of the first element and the function of the second element. This is all we have used here. So this is completely general, right? So anytime you have a relation defined as the equality of a function of the first element and the second element, that is always an equivalence relation, right? But we're dealing with a particular equivalence relation, and it's an equivalence relation defined by this set here. Okay, so we first need to clarify what this really means in order to make sense of this expression. So for that, what we're going to do first is we're going to decompose A into pieces. We first make the intersection with B complementary and then with B, right? So any set A has a part on B and a part on the complementary of B, right? And the union of both reconstruct the whole set A. By the way, this is what we usually denote A minus B, right? Okay, if this is so, then when we make the intersection X with A, what we're doing is we're making the intersection X with A and an intersection with BC, and then the union with, well, this is just a distributive property, right, of the intersection with respect to the union, and then we have X intersection A intersection B. Okay, but the nice thing is this whole set here, no matter how complicated it is part of B, right? Because it's an intersection with B, so it's part of B. So this is a subset of B. So when we make the union of this set with B, which is the definition of f of x, right? What we have is this, which from now on we're going to denote like this, okay? Then we have this, which is a subset of B, intersection B, and then we have B. And this whole thing, a subset of B union with B, is just B. So f of x is just x intersection with A minus B union with B. All right? Okay, now what does it mean f of x is equal to f of y? Well, what it means is, according to this new way that we have expressed the relation, is x intersection with a minus b, okay, union b is equal with y intersection a minus b union with b. However, this part here is the same in both sides, and this part here is part of the complementary of b. It's outside b, right? So for these two things to be equal, only this part need to be equal. So if this is equal to this, then the whole expression is equal. So the equality reduces to this: x intersection with a minus b equal to y intersection with a minus b. Okay, so let's put it this way: x is related to y if and only if this thing happens, which is a different way of writing the same expression. And this is actually the way in which the function of problem 10 was defined, right? Problem 10, we define the relation with the intersection with a fixed set. This is a fixed set, right? A and b are fixed, so a minus b is a fixed set. So we define this relation with the intersection with this fixed set. All right. So according to that, if you remember, the equivalence classes of this are defined by all the subsets of, well, all the subset of the set parts of E, okay, all the elements of parts of E, which are subsets of E, such that the intersection with A minus B is a given set C. And this C, of course, is a subset of A minus B, right? Okay, because it's the intersection with that. And we can use this C as the representative of the class, right? So these are the classes of equivalence here, right? So, and we saw that there is a bijection between the classes of this set, or well, which is the quotient set PE with the equivalence relations F. There is a bijection with parts of A minus B, right? And the bijection is this: we take the representative of the class that is in A minus B. Okay. So this answers the first question. Now let's go for the B, right? So let's go back and read what B is. Okay. For B, what we have now is a different function, gm, right? Which defined on any set x is, well, pretty much as the other one, right? Only that m now is different, so we can pick different m's here, right? So in particular, when m is a, we recover the function that we had here, the function f, okay? Now the question is, what are the conditions on m so that these two functions are the same? So the function we're defining here is equal to the function that we're defining here. Well, of course, if m is a, they are equal, but is that the only possibility, or there are other possible m's for which this is also true? And if they are, what is the condition for those m's, right? Okay, and once we determine which m's satisfy this, we need to determine what is the smallest, if such thing exists, right? Okay, so let's do that, right? And for that, what we're going to do is the following. Well, we know that according to the rewriting we've made, f of x is also x intersection with a minus b, which means that gm of x, which is defined the same way, is going to be x intersection with m minus b, right? So the condition that these two things, these two functions are equal is of course that m minus b is equal to a minus b, which means that the part of m that does not belong to b has to be the same as the part of a that does not belong to b. So for instance, just to make you, so that you have a clear picture of what I'm talking about, imagine that this is the set A and that this is the set B, right? So this is A and this is B. So this is the part of A which is not in B, okay? This is A minus B. So this part must be the same, right, in both cases. But M can contain some more part of B. So for instance, this set here, all these p's plus this piece here could be the set M, right? And if this is the set M, this difference would be the same. So you see, of course, if M is equal to A, this is an equality, but also for different M's, for M's that are bigger than A, this can also be an equality, right? So there are many of them, right? So the condition is only that the part of M that is not in B is the same as the part of A that is not in B, so that this part coincides. Otherwise, I mean, the other part can be whatever, arbitrary. All right. So what is the smallest possible M that satisfies this? Well, according to this, is clear, right? Is the one that does not have any part here contained in B. So the smallest possible M is precisely A minus B. So this one here. As long as this part coincides, this is okay. Because if the M is equal to this, of course, M minus B is equal to A minus B, right? It's A minus B, but we have already removed all the elements of A which are in B, so this is redundant, so this is just A minus B again. Okay, so that's the smallest one. By the way, let me just make a remark about the equation that we have found here, right? The function f that we have defined in part A, right? It's just a couple of remarks, just to illustrate two particular examples. So we can consider a particular example in which the intersection of A and B is the empty set, right? Remember, the function f is defined as x intersection A union B, which turns out to be x intersection with, well, no, it's not equal to that. It's not equal to that. Yeah, okay. But the equivalence fx with fy, this equivalence can be rewritten as x intersection A minus B equal to y intersection A minus B. All right. Now suppose that A intersection with B is empty, right? So there are no elements in A that belongs to B. So A minus B is just A. So what we have here is x intersection A is equal to y intersection A. And B becomes irrelevant, completely irrelevant in this equality. Plays no role whatsoever, okay? On the contrary, suppose that now what we have is the situation in which A is a subset of B, which is the opposite situation to this one. Here A and B do not have any element in common. Here all the elements of A are common to elements of B, so it's totally inside B, right? Okay, then A minus B is precisely the empty set, right? Because all the elements of A are in B, so if we subtract them all, then we're left with nothing, right? So this equality becomes x intersection the empty set is equal to y intersection the empty set. But x intersection with the empty set is of course the empty set, right? Because there's no elements in common here, and y intersection with the empty set is also the empty set. So this equality is trivial. I mean, it's satisfied for every single x and y, every pair of x and y that you choose. So all the elements belong to the same class, right? All the elements belong to the same class. And then what we have is that there's only one class, right? E is the only class. Parts of E. Part of E is the only class in the set, right? So all elements belong to the same class. Okay?